Section 1 Introduction. Let's dive into the world of vision and language models. These models are typically designed to take an image and some text as input and generate text as output. A good example of this is the BLIP2 model. This format is quite versatile and can be used for tasks like image classification and visual question answering. However, there's a limitation. These models usually work with a single image as input. Now, imagine a model that can handle a sequence of images and text, not just a single image. This is where autoregressive vision language models come into play. They offer a lot more flexibility. For instance, they can handle demonstrations for a new task, which allows for few-shot, in-context learning or multi-round multimodal chatbot interactions. Models like Flamingo, CM3, Cosmos 1, PALME, and multimodal GPT-4 have shown great performance across a variety of vision language tasks. But there's a catch: these models are closed source. This means that their weights, training data, code, and hyperparameters are proprietary, which limits the academic community's ability to conduct research on them. There are open-source alternatives like LLAVA, Llama Adapter, BLIP2, and MPLUG-OWL, but they only work with single images and are often trained on curated datasets like COCO instead of web data. In this report, we share our experience in building an open-source version of the Flamingo models, which we've named OpenFlamingo. We've followed the same approach as Flamingo, enhancing the layers of pre-trained language models so they can cross-attend to the outputs of a frozen vision encoder while predicting the next token. We trained our cross-modal module on web-scraped image text sequences using two open-source datasets, LAION2B and multimodal C4. We used publicly available components to build our stack, including CLIP as a vision encoder and open-source language models as decoders. OpenFlamingo is a family of 5 models, ranging from 3 billion to 9 billion parameters, with both standard and instruction-tuned language model backbones. When we tested these models across 7 evaluation datasets, the OpenFlamingo3B and -9B models achieved 85% and 89% of the performance of their corresponding Flamingo models. We've made the models and code open source for everyone to use and explore. Section Summary. The introduction discusses the limitations of existing vision language models that only take a single image as input and are closed source, which hinders research on their performance and safety. The authors present OpenFlamingo, an open-source reproduction of the Flamingo models, which allows for an arbitrarily interleaved sequence of images and text as input. The OpenFlamingo models, ranging from 3B to 9B parameters, achieve 85% to 89% of the performance of the corresponding Flamingo models on various evaluation datasets. Section 2 Related Work. In this section, we'll discuss the related work and our approach to generative vision language models. These models generate text based on a sequence of images and text. While some models, like BLIP2 and LLAVA, can only use one image at a time, autoregressive vision language models can handle sequences of images and text. This allows them to learn in context. We decided to replicate the Flamingo model because it's particularly good at this kind of in-context learning. In fact, the Flamingo model's performance improves consistently when it's given up to 32 examples to learn from. This is different from other models, like Cosmos 1, which only improve up to 4 examples and then start to perform worse with more examples. However, these autoregressive vision language models are usually trained on datasets that aren't publicly available. For instance, the Flamingo model uses the Align and M3W datasets, which are both closed source. To overcome this, we've used the LAION2B and multimodal C4 datasets, which are open source and similar to the original datasets. We've also created our own versions of the Flamingo model, which we call OpenFlamingo. These models use different datasets and language models, but they follow the same basic architecture as the original Flamingo model. Our OpenFlamingo models work by predicting the next piece of text based on the previous text and the most recent image. They use a technique called cross-attention to link the text to the corresponding images. To process the images, we use a vision encoder to extract features and then pass these through a trainable resampler. Before we start, we mark the locations of the images in the text with special tokens. We also add tokens after the text that follows an image. For example, if we have a sequence that includes an image followed by the text, "Hello World," we would preprocess it to look like this: less than image greater than hello world less than, end of chunk, greater than. We've created 5 different OpenFlamingo models, each with its own language model and number of cross-attention layers. All of these models use the same vision encoder, and in most cases, the image and end of chunk tokens are trainable. However, for the OpenFlamingo4B models, all tokens are frozen due to issues with gradient masking. At this time, our models don't support video inputs, but we're planning to add this feature in the future. Section Summary. Generative vision language models like Flamingo can generate text based on image text sequences, and Flamingo has strong in-context learning abilities. However, Flamingo relies on closed-source datasets, so we use open-source datasets like LAION2B and multimodal C4 to train our OpenFlamingo models. These models predict the next text token conditioned on previous text tokens in the last image, using dense cross-attention modules and a frozen language model. We do not support video inputs yet, but we plan to explore that in future work. Section 3.2 Training Data. We train our models using a combination of image-text pairs and sequences of images and text that are interwoven. We use a method called web dataset format to randomly select parts of our dataset for training. For the Flamingo model, we use Align, a proprietary dataset that contains over 1 billion individual images, each paired with a brief alt text caption. However, for the OpenFlamingo model, we replace Align with LAION2B, an open-source dataset that we've gathered from the web. This dataset contains 2 billion pairs of images and text, as shown in Figure A. We only use a portion of the English language subset and limit the captions to 32 tokens. All the image text pairs in LAION2B have a cosine similarity of at least 0.28, as determined by clip-vit-b, 32. In addition to image text pairs, we also train Flamingo using M3W, an internal dataset that we've scraped from the web. This dataset contains 43 million sequences of images and text that are interwoven. We replace M3W with multimodal C4, MMC4, an open-source dataset that contains 101 million interwoven samples, as shown in Figure B. Unlike M3W or OBELISC, which directly parse HTML documents to extract multimodal sequences, MMC4 uses clip to softly align images with sentences in a document. To ensure the quality of our data, we exclude images if their cosine similarity with the subsequent text is less than 0.24, as determined by clip-vit-l, 14. Sequences contain between 1 and 6 images, with a median of 2 images. To promote learning from sequences with multiple images, we discard sequences with only 1 image half of the time. The resulting distribution is shown in Figure. More information on MMC4 filtering can be found in the appendix. For the OpenFlamingo-4B models, we also experimented with training on synthetic data generated by ChatGPT, as shown in Figure C. These 417,000 image text sequences were created by prompting ChatGPT to generate a sequence of interwoven text and image alt texts, which stand in for images. The alt texts are used to find corresponding images from LAION5B. More details about the prompting and data construction process can be found in the appendix. The median number of images per sequence is higher than in MMC4, while the median number of text tokens is lower, as shown in table. We make these sequences available through the Section Summary. During training, our models are trained on a combination of image text pairs and interleaved image text sequences. We use different datasets such as Align, LAION2B, and MMC4 to provide a diverse range of training examples. Additionally, we also experiment with training on synthetic data generated by ChatGPT, where image alt texts are used to retrieve corresponding images from LAION5B. Section 3.3 Training Details. We've trained our OpenFlamingo models using a combination of 60 million interleaved examples, which include both MMC4 and ChatGPT generated data, and 120 million LAION2B examples. To give you a sense of scale, these 60 million interleaved examples are made up of about 240,000 ChatGPT generated sequences and nearly 60 million MMC4 sequences. However, some models only use the 60 million MMC4 examples for training. The training process involves predicting the next token in a sequence and optimizing this process using a method called AtomW. We start with a gradually increasing learning rate, which we then keep constant at 0.0001 for the rest of the training. We also apply a weight decay of 0.1 to the dense cross-attention layers to prevent overfitting. The batch size for LAION2B is twice that of the interleaved dataset, which may or may not include ChatGPT-generated sequences. We've set the loss weights to the default Flamingo values of 1 for MMC4 and 0.2 for LAION2B. We also accumulate gradients over both datasets between optimizer steps. We've used a distributed training approach, utilizing 64 GPUs spread across 8 nodes on Stability AI's cluster. For the OpenFlamingo-4B models, we've used model sharding with fully sharded data parallel, while other models were trained using only data parallel. In terms of loss curves, we've noticed that after an initial improvement, the MMC4 loss decreases very slowly. We think this might be because MMC4 sequences often include long paragraphs between images, so most text tokens can be generated without referencing the image. This means the loss might be more influenced by whether the frozen language model can fit unrelated paragraphs of text. We've evaluated OpenFlamingo on 7 vision language datasets, which include captioning, like Coco and Flickr 30K, visual question answering, like VQA V2, OK VQA, text VQA, VizWiz, and rank classification, like hateful memes. We've measured performance at 0, 4, 8, 16, and 32 in context examples. The evaluation was done in automatic mixed precision, with linear layers computed in bfloat16. Section summary. The OpenFlamingo models were trained using 60 million interleaved examples, consisting of both MMC4 and ChatGPT generated data. The training objective was next token prediction, optimized with AtomW and a constant learning rate of 1e4. Weight decay was applied to the dense cross-attention layers, and distributed training was conducted using 64 GPUs across 8 nodes. The models were evaluated on 7 vision language datasets, including captioning, visual question answering, and rank classification, at different numbers of in-context examples. Section. Selecting in-context examples. We're going to discuss how we selected in-context examples for our evaluation. For each example we evaluated, we randomly picked in-context examples from the training data. We also evaluated OpenFlamingo using a method called retrieval-based in-context example selection, RICEs, which you can find more about in the appendix. We used the same dataset splits for our evaluation as those used by previous researchers. We ran each evaluation 3 times, each time randomly selecting different in-context demonstrations. We then averaged the results to get our final scores. For tasks that required captioning, we formatted demonstrations as less than image greater than output, caption, replacing caption with the actual caption. For visual question answering, VQA, we formatted examples as less than image greater than question, question, short answer, answer. For hateful memes, we presented the model with less than image greater than as an image with text written on it. Is it hateful? Answer, answer. In zero-shot evaluations, we provided the model with 2 in-context examples, but without their images. For classification tasks, we used an ensemble approach, averaging the logits across 6 permutations of the in-context examples. We used a beam search with 3 beams to evaluate captioning and VQA, stopping generation at 20 tokens for captioning, 5 tokens for VQA, or whenever the model produced an end-of-chunk token. For hateful memes, we calculated the log likelihood of the answers, yes and no, and chose the most likely one. We used different metrics for different tasks. For captioning, we used the CIDR score. For VQA, we reported the VQA accuracy, which is the exact match accuracy over a set of ground truth answers. For hateful memes, we calculated the area under the receiver operating characteristic curve, AUC-ROC. In our results, we compared OpenFlamingo and Flamingo models using 0, 4, and 32 in-context examples. On average, OpenFlamingo models achieved more than 86% of the performance of their corresponding Flamingo models. In the 0 and 4-shot regimes, OpenFlamingo models came close to or matched Flamingo performances on several datasets. For instance, OpenFlamingo9b improved upon Flamingo 9b's zero-shot performance on VQA V2 and Coco. However, OpenFlamingo models were notably weaker than their Flamingo counterparts on OK VQA and Text VQA. For example, OpenFlamingo9b underperformed Flamingo 9b in zero-shot evaluations by 6.9 percentage points on OK VQA and 7.8 percentage points on Text VQA. OpenFlamingo3b also underperformed Flamingo 3b by 4.6 percentage points in zero-shot VQA V2 accuracy. The reason for the generally low VQA performance is unclear, but we discuss possible reasons later in the paper. Section summary. In this section, the authors describe their methodology for selecting in-context examples and evaluating their model. They sample in-context examples randomly from the training split and use retrieval-based in-context example selection for evaluation. They evaluate their model on different datasets and use different prompts and decoding parameters for each task. The results show that OpenFlamingo models perform well compared to Flamingo models in most cases, but they underperform in certain datasets like OKVQA and TextVQA. The reason for this lower performance is unclear and requires further investigation. Section. Extrapolating to more in-context examples. We're going to delve into more examples that are in context. In our graph, we've plotted how performance changes based on the number of in-context examples. We've noticed that the OpenFlamingo3B and -9B models generally get better as the number of in-context examples increases. However, the rate of improvement isn't as high as with the Flamingo models. In fact, if you look at the bottom right corner of our graph, you'll see that the gap between OpenFlamingo9B and Flamingo 9B gets wider as the number of in-context examples increases. We think this might be because our pre-training data is mostly made up of sequences with few images. In contrast to the -3B and -9B models, which generally get better with more in-context examples, the OpenFlamingo4B models surprisingly perform worse after 4 or 8 shots. These 4B models use red pajama language models instead of MPT backbones, and they also use frozen image and end-of-chunk embeddings. We're looking into the effect of the latter. When it comes to model size, OpenFlamingo9B usually performs better than smaller models, except on hateful memes and when there are a lot of in-context examples on Flickr 30K and TextVQA. However, OpenFlamingo4B models often perform worse than the smaller 3B models, including on Flickr 30K, hateful memes, TextVQA, and VizWiz. We've also been looking at the effect of language instruction tuning. We've trained two OpenFlamingo models at each of the 3B and 4B scales, one model using a base language model, and one with an instruction-tuned variant of the same language model. We've noticed that the instruction-tuned variants of MPT1B and REDPAJAMA3B generally perform better than the base models. This difference is most noticeable for Red Pajama 3B. The fact that language instruction tuning can be transferred to vision language tasks has been reported before. We've also compared each model's performance to the fine-tuned state-of-the-art performance, as listed on June 19, 2023. OpenFlamingo9B averages more than 62% of fine-tuned state-of-the-art performance with 32 RICEs selected in context examples, compared to 72% achieved by Flamingo 9B. For more details on the fine-tuned state-of-the-art models, see our appendix. Section summary. The performance of the OpenFlamingo3B and -9B models generally improves with the number of in-context examples, but at a slower rate compared to the Flamingo models. The OpenFlamingo4B models, on the other hand, unexpectedly degrade in performance after 4 or 8 shots. The OpenFlamingo9B model generally outperforms smaller models, except for certain cases, while the OpenFlamingo4B models often underperform the smaller 3B models. The instruction-tuned variants of the language models generally outperform the base models, particularly the REDPAJAMA3B model. Lastly, the OpenFlamingo9B model achieves more than 62% of the fine-tuned state-of-the-art performance with 32 in-context examples, compared to 72% achieved by the Flamingo 9B model. Section 5.1 Frozen Embeddings. In Section 5.1, we noticed that the OpenFlamingo4B models didn't perform as well as the 3B models on most datasets. One significant difference between the 4B models and the 3B and 9B models is that the 4B models' image and end-of-chunk embeddings are randomly initialized and then kept constant, rather than being trained. We explored the impact of this difference by training smaller models using OPT125M as a language model on 20 million interleaved samples, which is about a third of the full training. We found that keeping the image and end-of-chunk embeddings constant led to a 4.6-point decrease in the CIDR score for zero-shot COCO and a 12.1% decrease in accuracy for zero-shot VQA-V2. This suggests that keeping these embeddings constant could affect the performance of the models on other tasks. In Section 5.2, we used the VQA-V2 validation set to check the model's ability to answer visual questions. We noticed that while the performance on the COCO dataset steadily improved during training, the progress on the VQA-V2 dataset was more flat. This is consistent with what others have reported. We also found that changing the language model backbones had a significant impact on the VQA-V2 performance, even though additional training didn't have much effect. For example, switching from OPT1.3B to MPT1B, instruct, increased the zero-shot performance by nearly 10 percentage points. We think that the choice of language model could have a similar impact on other visual question answering tasks. We also identified some common issues with the OpenFlamingo models. For example, they had difficulty with counting. On the VQAV2 validation set, the OpenFlamingo-09B model only got 30.5% of questions with numerical answers correct, compared to 70.6% for yes/no questions. The models also tended to be too verbose, which is a problem because the scoring for visual question answering tasks requires exact matches. Finally, the models often focused on the main object in the image, even when the question was about a different object. Section summary. The OpenFlamingo-4B models underperform compared to the 3B models due to the frozen initialization of the less than image greater than and less than end of chunk greater than embeddings. Freezing these embeddings leads to a drop in performance for zero-shot COCO and VQAV2 tasks, indicating that frozen embeddings can impact downstream trends. Additionally, the OpenFlamingo models struggle with counting and tend to be too verbose in their answers, while sometimes focusing on the central object instead of other objects in the image. Section 5.3 Applications of OpenFlamingo. We've seen several applications of our OpenFlamingo platform. Various models have been built using this platform as a foundation. For instance, we've adapted OpenFlamingo to work with Mimikit, a dataset that includes multiple images and videos for instruction following. This adaptation resulted in the creation of Otter, a multimodal assistant. We've also launched Multimodal GPT, another model based on OpenFlamingo, which has been fine-tuned to handle both visual and language-based instructions. We're optimistic that the community will continue to find value in and use models developed with OpenFlamingo. However, it's important to note that OpenFlamingo models do have their limitations. They share the same potential pitfalls as the language models they're built upon. Specifically, these models are trained using data scraped from the web, and they haven't been fine-tuned with a focus on safety. As a result, they might generate outputs that are unexpected, inappropriate, or even incorrect. We're committed to further exploring the safety aspects of autoregressive vision language models like OpenFlamingo. Section summary. Multiple models have been developed on top of OpenFlamingo, including Otter, a multimodal assistant fine-tuned on a multi-image, video instruction dataset, and Multimodal GPT, an OpenFlamingo model instruction fine-tuned on both vision and language instruction datasets. However, it is important to note that OpenFlamingo models carry the same risks as other language models, as they train on web-scraped data and have not undergone safety-focused fine-tuning, which may result in unexpected, inappropriate, or inaccurate outputs. Further investigation into the safety properties of autoregressive vision language models like OpenFlamingo is needed.